Okay, so I guess let's get started with part two. Oh, Po-Ling, some of the audience were asking if you'd be willing to make your notes available.
Sure, yeah.
Okay, thank you. All right, so let's get started.
Okay, great. So the next lecture will be about robustness. So here's the reference by Chen, Gao, and Ren, a general decision theory for Huber's epsilon contamination model. In 2016. So we'll be focusing on lower bounds when we have some form of robustness of our estimators. So here's a little bit of background on Huber's epsilon contamination model. So this was the most classical form of contamination model in robust statistics. So we suppose that we have IID observations from 1 minus epsilon p plus epsilon q. And the goal is to estimate theta of p, where q is an arbitrary contaminating distribution. Okay, so we'll define a minimax risk. So the minimax risk is going to be R sub, let's say, Huber of script P, the loss function L, and the level of contamination. And this is the infimum over theta hat, supremum over the true distribution, as well as the contaminating distribution. Expectation, where X is coming from 1 minus epsilon p plus epsilon q, and now we have n IID observations. L of theta hat of x, theta of p. So just remember that we always have IID observations. It's a little bit awkward to keep writing this n-fold product, but I wanted to keep the notation consistent with the last lecture. So as before, we assume that the loss function L is of the form phi composed with rho. Okay, so here's a definition. So lower bounds are in terms of this notion of modulus of continuity. So the modulus of continuity, and this is a notion that comes from Donahoe and Liu, 1991, is defined by omega of epsilon p is equal to the supremum rho of theta of p1, theta of p2, such that total variation distance between p1 and p2 is bounded by epsilon over 1 minus epsilon, and p1 and p2 is in script p. Okay, so the result that I'll state in a moment tells us that the minimax risk, so the hardness of this problem, involves this quantity omega. And just to give you an idea of why this makes sense, so what we want to know is how hard is it to distinguish two distributions, right? So we're measuring everything in terms of the loss L, which is really kind of some version of rho. Rho tells us how far away the thetas look when the two distributions are close. And closeness is measured in total variation sense. And this, I'll mention a little bit at the very end about how you could think about other distances instead. The reason why we look at the total variation sense is very related to the fact that we are in Huber's epsilon contamination model. I guess let me write this down. So you can think about this quantity here as the Huber epsilon ball. Now, Huber isn't really a distance, but you can think about these distributions as anything that's kind of within this Huber distance. And it turns out that any of these contaminated distributions also lie inside the total variation epsilon ball. And that's why we see total variation coming up here. Okay, so with this definition, we have the following main result. The theorem is that for any level of contamination between 0 and 1, the minimax risk satisfies the bound R sub Huber, script P, L epsilon is bigger than or equal to the max of R sub Huber, P, L0, and 1/2 phi of the modulus of continuity over 2. Okay. So one other thing I wanted to say was, let's go back to this definition of minimax risk. So for the third and fourth lectures, I'll be talking about minimax risk, where the estimator itself is constrained to being something, whether it's differentially private or computable in polynomial time, etc. This characterization is a little bit different, because here we're still looking at all estimators, but we've changed the notion of risk a little bit. So now we're allowing our x's to come not from just a clean distribution, but some contaminated distribution. So in some sense, this is not really a robustness constrained estimator. We're not requiring data hat to be robust, but this is saying that we want an estimator to perform well, even when the data actually happen to come from some perturbation. And maybe for those of you who work on adversarial risk in the modern machine learning sense, this will be quite familiar to you. So you want an estimator that performs well even when data are contaminated. Therefore, you would to ask, what's the best possible estimator I could get under this slightly perturbed distribution? Okay, so going back to our theorem. So our theorem says that we want to look at this Huber risk, and we can take the max of 2 quantities. And really, the first quantity is sort of trivial. So let's go through the proof of this. Okay, so the first remark is that the fact that R Huber PL epsilon is greater than or equal to R Huber PL0 is trivial. So this is just the usual risk. So this is the non-robust, or I'll just say usual minimax risk. All right, because all we're doing here is we're saying, well, it's as if we didn't add any contamination at all. So Q is just the same as P. Okay, so there's really just one thing to prove, and that is that this second bound holds. Okay, so we will focus on proving the second lower bound. Okay, so consider a pair P1, P2, which solves the program supremum over row of data P1, data P2, such that the TDP distance between P1 and P2 is less than or equal to epsilon over 1 minus epsilon. Okay, so this is really just saying, if you go back to the definition of modulus of continuity, consider a pair that maximizes this row, which corresponds to the solution of modulus of continuity. So maybe I'll write this as a little lemma, because it's kind of a side result. So lemma is that the Huber epsilon balls around P1 and P2 intersect. So there exists, maybe I'll say that 1 minus epsilon times P1 plus epsilon times Q1 equals P prime equals 1 minus epsilon P2 plus epsilon Q2 for some Q1 and Q2. Okay. And let me quickly jot down what this proof is. You can check for yourself that this construction works. So we will construct the distribution. So we will construct Q1 and Q2 to make, it's called a star hold. Okay, so so there exists epsilon prime less than or equal to epsilon, such that rho of theta P1, theta of P2 equals omega of epsilon script P. and total variation distance between P1 and P2 is equal to epsilon prime over 1 minus epsilon prime. Okay, so these guys maximize this program, and that means that we have to actually achieve what the modulus of continuity is. However, the TV distance might be smaller than epsilon over 1 minus epsilon, so there's some epsilon prime for which we have equality there. So now define the density functions P1 equals dP1 over dP1 plus dP2, and P2 is dP2 over dP1 plus dP2. So this is just a rescaling of the densities. And then define Q1 and Q2 by the density functions dQ1 over dP1 plus dP2 is equal to little p2 minus p1 as indicator that p2 is bigger than or equal to p1 divided by the total variation distance between p1 and p2. And dq2 is defined similarly. dp1 plus dp2 is equal to p1 minus p2, indicator that p1 is bigger than or equal to p2 divided by the total variation. Okay, so so you can check that dq1 and dq2 integrate to 1 and star holds. Okay, so I'm not going to go through the details of verifying this computation, but maybe just to draw a picture. So imagine that you have P1 and P2. Let's say this one is P1 and this one is P2. Okay, so you want to construct somebody who's in the epsilon, in the Huber ball. So you think about shrinking down these densities by 1 minus epsilon, and then adding something else to them. Maybe I should have different colors. Well, okay, fine. So we shrink them down, and then we have to add something else to each of these distributions, and then we get this distribution, which is a shrunk version of P1 plus something else, and the shrunk version of P2 plus something else. So the something else's that we add depend on whether P2 is bigger than P1 or P1 is bigger than P2. So if we're thinking about what to add to the distribution of P1, then we add things only on the set where P2 is bigger than P1. Okay, so we sort of shrink it down, we add things here. And then for the other guy, we also shrink it down, we add things here. And things work out so that the expressions are exactly what we should be adding on. Okay, but I won't dwell on that. So what's the point? So we have these two distributions, P1 and P2, and we know that the Huber balls intersect. Now we're going to play around with this statement. Okay, so let delta be bigger than 0. That's the end of that proof. So now we go back to our minimax risk quantity. Supremum P in script P and over all contaminations Q. Probability that X is distributed as 1 minus epsilon P plus epsilon Q to the N. And we're interested in the quantity where this guy is rho of theta hat of X, theta of P is bigger than or equal to delta. Okay. So we're really interested in the loss function L, but later we're going to put a phi function there to make it equal to L. Okay, so let's play with this guy here, and this is bigger than or equal to 1/2 of the sup over Q. So here we're going to take an average of two possible values of P, and which values of P will we choose? Well, of course we'll choose P1 and P2 because that's just what we were dealing with a moment ago. So sup over Q of probability X is coming from 1 minus epsilon P1 plus epsilon Q to the N, rho of theta hat of X, theta of P1 bigger than or equal to delta, plus 1/2 sup over Q, probability of X coming from 1 minus epsilon P2 plus epsilon Q to the N, rho of theta hat of X, theta of P2 bigger than or equal to delta. Okay, so we've used this trick where Of course, the soup is bigger than or equal to the average of any of the points that lie in the set. And in particular, we know that a particular instantiation of a contamination distribution is what we call P prime, that common distribution that lay in both sets. So this is bigger than or equal to 1/2 of, oops, what did I want to do? This is 1/2 of the probability that X is coming from P prime, rho of theta hat of X, theta of P1 bigger than or equal to delta, plus 1/2 probability that X is coming from, again, P prime, because P prime lived inside the second contamination ball as well. Rho of theta hat of X, theta of P2 bigger than or equal to delta. Let's make this a bit clearer. Okay. So now we're going to take delta to be a particular value. Let's call it 1/2 of the modulus of continuity. Then by the triangle inequality, the right-hand side is further lower bounded by 1/2 probability X coming from P prime, rho of theta hat of X, theta of P2. Oops, no, that's not what I meant. I meant theta of P1, theta of P2 bigger than or equal to 2 delta. Right, and this is because, well, certainly if the distance, because rho satisfies the triangle inequality, so certainly if the distance between P1 and P2 in theta sense is at least 2 delta, then at least one of them has to be bigger than delta. Okay, but now remember that we actually chose P1 and P2 to be 2 delta separated. Sorry, well, that's not, okay, so what did we do? I don't want to confuse you because we're not in Fano's inequality anymore at the moment. So what did we choose about P1 and P2? We actually chose these two guys so that this was an equality, right? So we chose, so because delta is 1/2 of the modulus of continuity, we want to ask, well, maybe I'll write this here. So this is equal to 1/2 probability X is coming from P delta, P prime to the N, rho of theta P1, theta P2 is bigger than or equal to omega of epsilon rho, right? This is by our choice of epsilon P. This is by our choice of delta, right? By our choice of delta. And in fact, we chose P1 and P2 to be 2 distributions that achieved the modulus of continuity in the supremum, right? So we said, consider P1 and P2, which optimizes this definition. Therefore, in fact, this is equal to the modulus of continuity. So we see that there's no probability here, and this is always equal to 1/2 times 1, or 1/2. Okay, so here, what have we done? We've gotten a bound of 1/2 on this probability. And of course, we want a risk, so we relate the risk to the probability using Markov's inequality. So therefore, by Markov, we have expectation under X distributed as 1 minus epsilon P plus epsilon Q to the N of L of theta hat X, theta of P. So the real risk will have a bunch of supremums on the left side, but let's not write them for now. This is bigger than or equal to, so Markov's inequality, I can put in whatever I want, and I'll put in this guy, times probability that L of theta hat of X, theta of P is at least phi of omega epsilon P over 2, right? And I'm not going to write down what the probability is taken with respect to, but it's the same thing. And this is equal to, so here's where I remind myself that L is equal to phi composed with rho. So this is phi of omega epsilon P over 2 times probability that rho of theta hat, theta of P is at least omega of epsilon P over 2, right? And this is exactly what I have calculated back up over here. So here delta was omega over 2, right? So So this is going to be greater than or equal to 1/2 times times phi of omega of epsilon. Actually, I think I probably need to take a soup first. So taking soup over P and Q on both sides and using the inequality above. So that was this inequality here, right? So we need to take a soup first because we have a soup of these guys. We get the minimax risk, R of H Huber, P L epsilon is at least 1/2 phi of omega epsilon P over 2. Okay, and that's what we wanted. So just to recap, we have gotten this second bound here, and therefore, if we want to calculate the bound on this guy, we can take the max of these two. I mean, really, you could derive any number of bounds that you want, right? And I guess what's interesting is that these two bounds are oftentimes, for many estimation problems, enough to give you a tight lower bound. And we'll see that in examples. And just to, well, you'll see this also in the examples, but at some level, this guy, the second bound is a population level notion. So it doesn't depend on the sample size n or the dimensionality. It will just depend on epsilon. And whereas this is the usual rate that we would get in minimax rates of estimation, like it might depend on p or n or some problem parameters. And what we'll see is that oftentimes you can just cleanly decompose the optimal rate as, let's say, something like root p over n max with epsilon. So let's see that in some examples so it makes more sense. Okay. Someone have a question?
Yeah, I have a question.
Uh-huh.
Up there where you like distribute the soup Q into like two different terms. Actually in that part, like do you just need to lower bound like soup Q by the mixture, which puts like 1/2 probability on like the Q1 and the Q2 constructed in the lemma.
Mm-hmm. So you're asking if that would be enough to prove the lemma?
I just saying like I'm not sure you could just distribute the soup Q into the two terms directly.
You mean right here?
A little bit up.
Uh-huh.
More up.
Mm-hmm. More up?
Yeah.
So we have the lemma here, right? So is it a question about the lemma or how we apply it?
Sorry, your screen was lagging a bit. Underneath the lemma?
Yeah, so we assume that the lemma is true, right? Then that gives us a distribution which is inside both balls.
Yeah, so at this calculation, in the very first inequality where you write soup Q is bigger than or equal to, and then two terms involving soup Q,
Mm-hmm.
I think you can't soup Q is two different terms.
I think it's fine. I'm not sure I see where the question is. Yeah, I mean, it looks fine to me, but I guess I'll take a second look at it before I release my notes and correct it if necessary. All right. Okay. So I guess I'll keep going. Okay, so let's go over the first example. So what examples are we going to do? We're going to do two examples. The first one is going to be Gaussian mean estimation, or I guess earlier I called it normal mean estimation. And the second one is going to be normal covariance estimation. So these are the two examples that we went through earlier. So the first one is normal mean estimation. And remember that in this case, we had xi's, which were IID, normal, theta, sigma squared I. And the result, well, so theta was going to be in RP. And from last time, from lecture 1, we have R sub, basically the usual minimax rate is equal to the usual minimax rate. We were looking in squared L2 norm, and this was omega of sigma squared P over N. Okay, so our theorem says that we can also calculate the modulus of continuity and take the max of both. So we will show that the modulus of continuity with respect to L2 norm is omega of sigma epsilon. Okay, then we'll get the bound of R Huber, P 2 norm squared epsilon is going to be omega of the max of sigma squared P over N and sigma squared epsilon squared. Okay, so just to remind you, well, the bound that we have is just conveniently right here. So it's order of phi of omega over 2. And I'm saying that we're going to show that omega is little omega is big omega of sigma epsilon. Phi is the squared is the squared function since we're looking at L2 squared. So we have to square the sigma epsilon, which is where we get sigma squared epsilon squared. Okay, so you see that here, this is where I said that you get some rate that depends on the sample size and dimensionality, and then some other rate that just depends on epsilon. And this rate is achievable using what's known as Tukey's median. And again, I'm not going to prove that this actually works, but Tukey's median is defined as the arg sup over theta in R to the P, infimum over unit vectors, 1 over n, sum I goes from 1 to n, indicator U transpose xi minus theta is bigger than or equal to 0. Okay, so let me just give you a pictorial illustration of what this is. So Tukey's median is a point that maximizes the data depth. So you can think about this guy as the data depth. And just as a picture, so if you're trying to figure out what the data depth of, let's say, this point is, then the depth is measured in terms of looking at a half plane and counting how many points happen to be sort of on one side of it. So that's where you get this infimum over all directions you could project in. This is the data depth. Then we take a supremum over all of the depths of all of the points, and hopefully that gives us some point that's kind of in the middle. Okay, so so it turns out that this rate is indeed achieved by an estimator, which is Tukey's median. Okay, so and maybe just interpret this rate. Well, it tells us that really, depending on the level of contamination, we either get the usual rate or we get something that just depends on epsilon. So if we had infinitely much data, then the first term would go down to 0, and the rate that we would get would just depend on epsilon. Otherwise, it says if epsilon is smaller than epsilon is smaller than root p over n, then it says if the contamination wasn't there. Okay, so the point of this example is to show how you would actually go about computing them. So we write omega epsilon p is equal to the supremum theta 1 minus theta 2. And 2 norm is such that total variation distance between the two distributions is bounded by epsilon over 1 minus epsilon. So this is just the definition. Remember, modulus of continuity is in terms of the metric rho, and rho was equal to the L2 norm. So it turns out, so remember, this is a Gaussian family, and we're dealing with total variation distances. And we have explicit formulas for KL divergences between distributions. So we can use Pinsker's inequality to write this as theta 1 minus theta 2, such that square root of 1/2 dkl p theta 1 p theta 2 is less than or equal to epsilon over 1 minus epsilon. This is by Pinsker's inequality. Okay. And this is now greater than or equal to. So we had a formula earlier for the KL divergence between distributions, between Gaussian distributions. And you can explicitly write this down. So you get supremum theta 1 minus theta 2 such that theta 1 minus theta 2 norm squared is less than or equal to 4 delta squared epsilon squared. Okay, so I think what happened here was I used the formula for the KL divergence between two distributions with mean theta 1 and theta 2. And from this, you have theta 1 minus theta 2 norm squared, as well as a factor of sigma squared. And the only reason why this is an inequality instead of inequality is that I think I got rid of the 1 minus epsilon term because I didn't want that. So then this is, of course, equal to 2 sigma times epsilon, right? And that's the rate we wanted. So I claimed that we had the modulus of continuity lower bounded by order of sigma epsilon. So we're done. Okay. So now let's do another example. So again, we see that, just to reiterate, well, how did we get the final lower bound, which ended up being tight? We got the lower bound by just taking the lower bound we would get from the usual method for minimax lower bounds. And in fact, it doesn't have to come from Fano, but in the first part of the talk, we derived this bound from Fano. And then we just need to calculate the modulus of continuity to get the second term. Okay, so the second example is covariance matrix estimation. And for this example, we take, remember, xi is distributed IID as normal 0 sigma. And what we had was that from last time, R sub Huber, I should say. So from lecture 1, we have R sub Huber of script P. Oh, sorry. Let me remind you that the set that sigma lived in was that we had, I'll just write it here. So the 2 norm of sigma was bounded by lambda. Okay, so we have the uncontaminated risk in spectral norm squared is equal to omega of lambda squared p over n. That's what we had last time. And now we will show that the modulus of continuity with respect to the spectral norm is omega of lambda epsilon. Then we have the lower bound. R sub Huber P 2 norm squared epsilon is equal to omega of lambda squared P over n, max with lambda squared epsilon squared. Okay. And this is again because squared spectral norm means that the phi function is the square function. So we need to square this guy. One other thing I forgot to mention is that in both of these examples, we're showing that the modulus of continuity is omega of lambda epsilon. So, you know, we could try to calculate the modulus of continuity exactly. That would be another problem to solve. But really, in order to get a lower bound, we just need to calculate a lower bound on modulus of continuity. And then, of course, to show that this bound is tight, then you would need to do your analysis of the algorithm that you claim achieves it. And because there exists an algorithm which achieves it, then that means that it's actually tight. Okay, so how do we go about doing this calculation? Oh, also this is achievable. So this bound is achievable using a generalization of the Tukey median. known as, or based on matrix depth. Okay, so in the case of the usual Tukey median, you're looking at projections of the data in one dimension, right? And when you're in the space of matrices, you need to do something a little bit different, but you calculate some notion of data depth for every matrix, and then you take the deepest matrix. And this is all in the paper by Chao Gao and co-authors. Okay, so how do we calculate the modulus of continuity? So consider the matrices. Sigma 1 equals lambda over 2 of the identity, and sigma 2 equals lambda over 2 identity plus e epsilon times e, where this guy is just a matrix with one entry that's non-zero. Okay. Then we can check that. Well, first of all, I won't even write this down. So you can check that both of these guys are in the class of matrices with spectral norm bounded by lambda. Namely, epsilon is the level of contamination, so the spectral norm of this matrix is bounded by 2, and therefore the overall spectral norm is bounded by lambda. But furthermore, you can check that there is an upper bound on the KL divergence. So we can check using the KL divergence formula for Gaussians, that dKL of P sigma 1, P sigma 2 is bounded by epsilon squared over 4. This is very easy to do actually, because these guys end up, I mean, if you have a normal distribution with this covariance and that covariance, then the components are independent. So you can really just ignore all of the remaining p-1 coordinates and just look at the KL between the first two. But in any case, so let's take this to be given. So then again, using Pinsker's inequality, which upper bounds the TV distance by the KL divergence, we have TV of P sigma 1, P sigma 2 is bounded by square root of 1/2 times epsilon squared over 4, which is bounded by 1 over epsilon, 1 is epsilon. Okay, so therefore, the modulus of continuity is going to be at least the distance between these two guys, right? And why is this? Well, remember, the modulus of continuity is the sup over rho between the two parameters. Rho here is a spectral norm of any pair of matrices, such that the TV distance is bounded by epsilon over 1 minus epsilon. So here we've chosen one particular pair. And this is because the two matrices have such a simple form, this is going to be exactly equal to lambda epsilon over 2. Okay, so that's what we want. We claimed that we had a bound on the modulus of continuity order of lambda epsilon. Okay, great. So that's the gist of how you come up with how you can create lower bounds for this robust risk. So now I just want to say two more things before I end. So these are kind of comments. Oops. So you might ask, well, what's with the Huber epsilon contamination and total variation distance? So what if you want to deal with other forms of contamination? And there's one that's very popular these days, adversarial contamination. Okay, so adversarial contamination says that you have xi, which are drawn iid from some distribution p, and then epsilon n are arbitrarily corrupted to form the new data set, which let's call x prime. Okay, so the minimax risk that you might be interested in here is infimum over theta hat, supremum over p in p, expectation x distributed as p to the n, supremum over x prime of loss function of theta hat applied to x prime theta of p. Okay, So why does this all make sense? Well, I'm generating my data from this clean distribution P. I have NIID samples. And then I want to know, well, now I have a supremum over X prime inside the expectation, because the adversary, after the X's are generated, the adversary can perturb arbitrarily. And then I calculate the loss between the estimator on the perturbed data and the true parameter that I care about. So the main remark I wanted to say is that the lower bounds via Huber epsilon contamination, via the Huber epsilon contamination mechanism apply here, can be applied here. Okay, so actually a lower bound can be written of the form R sub Huber of, let's say, script P, same L, and let's call it epsilon over 2. Okay, and let me just kind of argue this in words. So what we're doing when we calculate this adversarial risk is we're saying, well, I can choose the worst possible adversarial mechanism. And I'm saying that if you use a Huber epsilon contamination adversary where you draw most of your data from the clean distribution and an epsilon over 2 fraction from the contaminated distribution, then this is one possible case of an adversary. And the reason is that with high probability, if you have, right, so with high probability, is that right? Yeah, okay, well, something like this is correct. So you can simulate the action of the Huber contaminator using the logic is kind of twisted in my head, but the point is that one possible form of an adversary is where the Huber adversary just acts by drawing some fraction of data from the clean distribution and then some fraction IID from an arbitrary distribution. And for instance, in the case of Gaussian mean estimation, so in Gaussian mean estimation, the latter lower bound is also tight. Okay, so the point is that the adversary is in general a stronger form of contamination. So the lower bound that you would get could be bigger. So even though this is a valid lower bound, you could get a bigger lower bound in principle. But you can argue that the same estimator that achieves the lower bound for Huber contamination, which is the Tukey median, also achieves the bound that you would get in this case, meaning that this method of bounding is tight. Then the other form of contamination that I wanted to touch on briefly, because this is something that I've looked at a bit in my own work, is Wasserstein contamination. Okay, so historically, people have looked at Huber contamination because Huber was one of the key people in robust statistics, but you might consider other perturbations of a distribution. So instead, you can define the Wasserstein minimax risk as R sub was PL epsilon is equal to the infimum over theta hat. And now we're looking at a supremum over distributions W of PP prime less than or equal to epsilon. And now we draw data X from P prime N, L of theta hat of X, theta of P. Okay, so here, this is saying that rather than the Huber epsilon contamination ball, we're drawing from some distribution P prime, which is in the Wasserstein ball. Here, W denotes the Wasserstein distance. And in the particular case I want to mention, let's say it's the Wasserstein 1 distance, which can be written in terms of Wasserstein distance between P1 and P2 is the supremum over all 1 Lipschitz functions of expectation under X coming from P1 of f of X minus expectation X coming from P2 f of X. Okay, and then we can define the modulus of continuity. And now we'll call it omega W was of epsilon P. And this is equal to the supremum. And now it's going to look very similar to what we had earlier, except of course, there's no total variation distance anymore. So we have theta P1, theta P2, such that the Wasserstein distance between P1 and P2 is less than or equal to epsilon. Okay, so this is saying how close do the two parameters look for distributions which are now close in Wasserstein distance. And remember earlier we had total variation distance because that was directly related to the Huber ball. So one can derive, so we can derive the lower bound R sub was P L epsilon is greater than or equal to the max of R sub was P L 0. So here's the same thing where there's no contamination. And then the second term is 1/2 B of omega sub was of epsilon P over 2. Okay, so at least in terms of the syntax, this looks exactly the same as before, right? We have 1/2 phi of the modulus of continuity over 2. So really, what's special? Why am I stating this specifically for a Wasserstein 1 distance? Well, if you remember the way that the proof went for the Huber epsilon contamination ball, I needed, so the proof before and here as well, needed that if P1 and P2 optimize the modulus of continuity problem, program, which is this program up here, then there exists a distribution in both epsilon balls. Okay, so here we are looking in terms of Wasserstein epsilon contamination ball. And it turns out that in this case, it's very simple actually. Here for Wasserstein distance, P prime equals 1/2 P1 plus 1/2 P2 actually works. The mixture just works. And this comes from this duality form of Wasserstein distance, and you can just plug in what happens when you look at a mixture. Okay. And actually the same sort of argument would say that if we cared about, so you can think about a version of contamination where this is replaced by total variation distance instead of Huber ball. And I think the same argument would work where this is the TV ball and this is now TV. So you can play around with several different metrics. And maybe the last thing is that for Gaussian mean and covariance estimation with Wasserstein contamination, then you can actually show that the modulus of continuity is of the same order as in the TV case. That omega Wasserstein epsilon P is of the same order as omega Huber. So here, this guy was the Huber. Oops. Huber modulus of continuity from before. Okay, so the same bounds on the contaminated robust risk hold, and perhaps more interestingly, and the lower bounds are also tight. Can also be achieved. And in my own work, I've showed that this can be achieved using a notion of a Wasserstein GAN. Okay, so I'll end here, and I'm happy to take any questions on this lecture.
Okay, see a question back there.
Hi, Po-Ling. Great tutorials. I was wondering if you could comment a bit about the computational complexity of computing the Duke median.
Oh,
Really,
I don't know off the top of my head, but
or
I think it's like n to the p, but it is computationally intractable.
and are there computationally efficient estimators that get something close, or
Yeah, So, so I mentioned very briefly, like the last sentence I said was that I had done some work where I found computationally, well, where I studied the Wasserstein contamination model using Wasserstein GANs. So this was very much inspired by work by Chao Gao a few years ago, where he used total variation versions of GANs in order to try to simulate what the Tukey median is doing. So you could use something like that as your as a computational tool, and if such a method is able to actually find an optimum, then that will also give you a computationally tractable version of the Tukey median. There are some results too on let's see, I guess if your data are, I don't feel qualified to say this off the top of my head because I'm almost definitely going to say something wrong. But there are also various results where your data come from nice distributions, where you can get some sort of, some other estimators that also perform well. And I'm pretty sure at least one person in the audience has probably worked on this problem.
I see. In the worst case, could there be some kind of information computation gaps here, or?
Yeah, I mean, if your data are not coming from some nice distribution, like if you're just talking about computing the Tukey median, for sure.
Like, what about the robust mean estimation problem?
Yeah, it's possible. I don't know off the top of my head.
It has a information computation gap.
Sorry?
It does, yeah, robust sparse mean estimation. But without sparsity, the story is different. Yeah, I guess the short answer is it's complicated, but robust sparse mean estimation does. Yeah.
Mm-hmm.
Great, thanks.
Mm-hmm.
More questions?
Can I ask something from the Zoom? I don't know
Sure.
if that's okay. Yeah.
Mhm.
Thank you very much for the talk. So one question I had is like, is there like these results seem to be applying for like input distributions which are like product, right? So kind of product, like what if like for example the input's like a graph, or like, you know, has some graph structure, like is there like some mechanism to produce lower bounds for robust estimators in this case?
Yeah, well, I guess what I would say there is that in the first lecture, the bounds for Fano were stated in a very general form. I don't know off the top of my head of examples in which well, lower bounds and matching upper bounds have been studied when you don't have IID data. But in principle, yes, you could use the bounds from the very first part in much more generality.
But for the robust part?
Oh, for the robust part, I don't know off the top of my head. Yeah.
More questions from the live or Zoom audience? Okay, all right, in that case, I guess we'll wrap it up. Thank you so much, Po-Ling, for the great tutorials. One more round of applause.
Thanks.
And we'll resume at 2 p.m.